will be Yifei, who's going to be talking about star-forming dwarf galaxies.
Not too much. Let's see. Okay, how about now? Okay, great. Okay, hello everyone. I'm Yifei Luo. I'm a graduate student here at UC Santa Cruz. So I'm going to talk about this rather new survey, the Merian Survey, which is a new medium imaging survey, and the primary size case is dwarf galaxies, the dark matter, and feedback in those dwarf galaxies. So I should give all the credit to my collaborators here, so my thesis advisor, Alex Leopold, and Jenny Green at Princeton, which are the co-PI of this survey. So for those of you who are not familiar with Merian, Merian is a medium band imaging survey on the dark energy camera, DCAM. So the goal is to get a really large star-forming galaxy sample at redshift about 0.1 for 10 to the 8, 10 to the 9 solar masses. So to cover about 800 square degree within the HSC wide field. And the core science cases is to get the weak lensing signal around those dwarf galaxies constrained halo mass, and also characterize the stellar feedback in those dwarf galaxies. And at the right, I show 3 examples, very nice self-forming dwarf galaxy in our sample. You see the continuum from HSC color images and those highlighted H2 regions, emission line regions from Merian. So as I mentioned, there are 2 medium band imaging, two medium band filters for Merian, one capturing the H alpha, one capturing the O3. And we built those filters, and in my 2024 paper, which just published last month, I discussed filter design for Merian, so I wouldn't talk too much about it. So please, if you are interested, go to my 2024 paper. So the idea is for this mass range, 10 to the 8, 10 to the 9, as Richie just showed, the fringing fraction is really low. So for the few, galaxies in this mass range, they are basically all star-forming, and even for satellites, they are, 80% or even more star-forming. So most of them should have pretty strong emission lines that we can capture with our mid-band filters. So for Merian, we have already finished about more than 500 square degree with full depth, full color. Or still have some, observing run actually coming this Friday. But we are finishing pretty soon in 1 or 2 semesters. And this is a map, survey map for our field. And we have reduced the first set of the data. So we call Merian DR1. It contains 230 square degree with full depth, full color. So I show 3 example dwarf galaxy here. The GRIZY and N540 and 708, that's the O3 and H alpha filter, which is pretty nice. And if you subtract the continuum properly to get H alpha and O3 map, you can see very nice emission line map for those dwarf galaxies. I will talk about this a little bit more in a minute. But remind you, we will have 1,000 or 100,000 dwarf galaxies with those maps, which will be great. We can also run photo Z's. This is for lensing. We achieve decent photo Z precision with Merian emission lines and the HSC continuum. And we can measure lensing. So this is our preliminary lensing results. We detect a lensing signal around those dwarf galaxies with decent lensing signal noise with only 30% of Merian footprint. And if you do a very simple, maybe not correct way to fit an NFW, you can see on the star mass halo mass relation, they are line up pretty well with the previous literature but we are still doing more modeling, to make this more appropriate. And this session is about star formation, so I wouldn't touch much about this work. So instead, I will talk the other science case, the science interest, the feedback in star formation work. So as I briefly mentioned a minute ago, we could subtract the continuum basically between our N708 or N540, any of our medium filter, to subtract the continuum inferred from HIC broadband filter, so you can get a emission line map. So to calibrate this, to convince ourselves, we started with a spectroscopy sample, which all have existing spectra, from public survey and also our observations on CAC and Magellan and ESI. So if you go to those H-alpha maps, make a aperture photometry, match to the aperture of the fiber to measure H-alpha fluxes directly from the images and compare with the spectroscopy H-alpha fluxes, because they agree pretty well. So it's kind of reassuring. So we start with those H-alpha maps. So what we have done is to first look at the morphology. So we measure the morphological parameters. We start with the asymmetry on those H-alpha maps, also the continuum. So this is on the left is the asymmetry from the H-alpha map, and the right is the asymmetry from the continuum. And we correlate this with the star-forming main sequence, and we find a positive relation along the star-forming main sequence. That being said, the more star-forming galaxies on the star-forming main sequence will have more asymmetric morphology on both continuum and H-alpha. This has been found in continuum. For example, Hassan Yesef published a paper in 2021 also saying this with continuum, and we see even more asymmetric morphology with H-alpha maps. So this is kind of interesting result. We also measured a Gini M20 relation, well, not relation, more like the parameter space for H-alpha and continuum. So this was originally used to find a merging feature in more massive galaxies. So as you can see, this is the continuum, and this is for H-alpha. So for continuum, we don't have much merging pairs, and most of them are star-forming galaxies. But for H-alpha, it's much more, say, spread to this, the originally called merging region using the continuum. And we know, sort of, new H-alpha is kind of more, clumpy than the stellar disk. And if you correlate this Gini M20 and asymmetry with star formation, specific star formation rate, we find a very interesting trend. So blue is continuum, and red, orange is H-alpha. So if you look at the Gini coefficient for the continuum, that many people have been looking at, you don't see much trend with SSFR. But there's a pretty strong trend, especially for the highest SSFR spin. It's more concentrated if you have high SSFR. And also, there's a positive relation. This is basically the relation I showed for the last slide. There's a relation between asymmetry and SSFR. So if you only look at the H-alpha and break them into two mass spins, you can also see this kind of a relation. And to give you a more kind of a picture idea, so for me, our higher mass spin, that's basically the Milky Way mass, star-forming galaxies, 10 to the 9.7 to 10 to the 10.3. For high SSFR, they look like this. They're clumpy. They are kind of large because they are also large in mass, and less diffuse. For those, and also more asymmetric. And low SSFR in the same mass spin are less clumpy and more less asymmetric. This is also consistent with another work led by Xiaohan Wang, he talked about this in the next session. So this S2 parameter is also kind of like a symmetry plot clunkiness parameter versus C4000, also kind of like equivalent to the specific star formation rate. Well, not exactly the same, but similar. So we do also find a relation in this similar mass beam, 10 to the 9.5 to 10 to the 10. But this sample is using manga, so we also have the kinematic measurement, the lambda parameter, showing whether they are rotating or more dispersion supported. So we also confirm those more clunky, more star-forming low-mass galaxies are actually more dispersion supported. They're not actually, rotating. And many of them also show, kind of interactive disturb feature. So we saw a potential explanation to be they are disturbed by, interaction or even just, cold gas accretion, which also brings them, to be above the star-forming system. So this is consistent. However, manga cannot go to even low stellar masses with rather, statistically large samples. But how about those lower masses galaxies, 10 to the 8 to 10 to the 9 solar masses? We know they're more concentrated for high SSFR. They're kind of different from the high mass regime, high mass similar SSFR counterparts. So what's going on there? Can we get a kinematics measurement to further understand this? So to understand this, and also I should mention this, for this mass range is also kind of interested to test the dark matter. We know there's a lot of dark matter cores have been found in nearby dwarf galaxies with similar mass range. And one potential answer is due to the baryonic effect or stellar feedback to produce the dark matter cores by altering the gravitational potential. They are low mass. They are gravitational potential is rather shallow. So if this is true, and we found in some hydrosynths, there will be a correlation between the star formation, dark matter core, and also the gas kinematics. So to answer this question, we built another sample smaller sample with CAC DEMOS observation. So this is one example. So we put the DEMOS slit on about 100 low mass galaxies at redshift below 0.2. So this is not exactly Merian range, but we selected with this Cosmos 30 band photo Z and observed with the CAC DEMOS to get gas kinematics. We also did the mock observation in the fire tube simulation to get exactly as similar as possible observables for the H alpha velocity dispersion and SSFR. So there are 8 of low mass galaxy halos in fire tube, and we get about 100 snapshots for each simulation to get a large sample that we can look at. So this is the result. So y-axis is the ionized gas velocity dispersion. X-axis is the specific star formation rate, and we do observe a positive trend. So the blue points are from fire, and red points are from our observation, and there are some higher resolution galaxies from previous literature did a similar thing. So the point here is the observation simulation agree pretty well with each other in terms of this gas velocity dispersion versus SSFR relation. And you might notice there are lots of low SSFR points from fire, but not much from the observation. We need them to be star forming to measure the H alpha velocity dispersion. This could be biased, so if we take out all the low SSFR points from fire and refit this relation, and basically the result is the same. So we are not affected much by the incompleteness. So I will leave the summary here and take the questions. Thank you.
Any questions? Yes.
Very interesting. But my question is, HSC SSP also has several narrowband filters, right? So are you using those data as well, or?
No. So the thing is, the area is not that large. So for Merian, because the primary science goal is for lensing, so we need a larger, area, larger volume to get more samples. I agree for those detailed follow-up observations we might, but indeed we haven't included any alpha before. HSC we did not.
Yeah, right. But basically, what you are talking about here has nothing to do with the lensing stuffs, right?
That's true.
So
That's
why not use those as well?
Yeah.
Yeah.
Yeah, I agree.
All right, time for one more quick question if anyone has it. Okay, so let's thank Yifei and all the speakers again.